Welcome back, everyone, to another deep dive into the OEIS, the
Yes.
Online Encyclopedia of Integer Sequences.
It's a great resource.
It is.
Yeah.
We're tackling A000095 today. And
This one's really cool.
this one is a cool one.
Yeah.
It might just look like a simple list of numbers, but
Yeah.
it kind of takes us on a little bit of a mathematical journey.
Yeah, it really does. I mean, what's fascinating is how it acts as this like bridge
Yeah.
between abstract algebra and number theory.
Yeah.
You know, you start to see patterns and you connect areas of math that you wouldn't think are connected.
Right. And for anyone who maybe hasn't joined us before on these OEIS adventures,
Yeah.
can you kind of give us the quick rundown of like what the OEIS is all about?
Yeah, absolutely. So the OEIS is this massive online database of integer sequences. You can think of it like a digital library of numerical patterns. So mathematicians, anyone who's interested in this kind of stuff, can explore and contribute to this ever-growing collection of sequences.
Yeah.
It's a phenomenal resource. I mean, there's a lot of hidden structures and relationships within mathematics.
So where does A000095 fall in this like numerical library?
Right.
What makes this sequence so special?
So A000095 deals with the number of fixed points, something called MA as 0n, which is often written as that Greek symbol G-M-A-N of type I. Now, GMMA0n is a subgroup of the modular group. And I know there are a lot of terms there.
Yeah.
We don't have to go too deep into the technicalities of what a type I fixed point is. But just know that they represent specific points that remain unchanged under certain transformations.
So modular group sounds a little intimidating.
Sure.
Can you kind of break down what we're transforming here?
Yeah, it's a great question, and it's really more approachable than it might sound at first. Imagine the upper half of the complex plane, right? So it's two-dimensional. One axis is the real numbers. The other axis is imaginary numbers. And the modular group consists of transformations that just kind of shuffle around points in this complex plane. Almost like you're rearranging tiles on a very specific and mathematically interesting floor. These transformations are represented by matrices, which are arrays of numbers that have a specific form and a determinant of 1.
So if the modular group is like shuffling all these tiles on our complex plane floor, then gamma Rn is like a more specific subset.
Exactly. You're getting it. You're getting the hang of this.
With even stricter rules about how you can rearrange those tiles.
Exactly. So the matrices in gamma 0n have this additional property where the lower left entry is a multiple of n. And what's really neat is that our sequence A000095 actually counts the number of points that stay put during these specific gamma 0 shuffles.
I think I'm starting to get the bigger picture here. So we've got these transformations in the complex plane. And this sequence is giving us a way to count the fixed points. And it seems like we're starting to uncover some hidden order within all of this.
Precisely. And what's even more remarkable is that A000095 has a multiplicative property. Meaning we can calculate any term in the sequence just based on the prime factorization of...
Hold on. Prime factorization. Now you're speaking my language. Can you walk me through just like a quick example of how this multiplicative property works in practice?
Of course. So let's say we want to find a 10, right? The 10th term in the sequence. We know that 10 is 2 times 5. The rules for A000095 tell us that A2 is 2. And for any prime number that leaves a remainder of 1 when divided by 4, like 5 AP, is also 2. So to get a 10, we just multiply a 2 and a 5. So 2 times 2, which is 4.
That's pretty cool. So by knowing the prime factors and following a few simple rules, we can calculate these seemingly complex terms. What other interesting properties or patterns pop up in A000095?
Well, there's one more really intriguing fact. It turns out the asymptotic mean of this sequence is 2pi.
Wow.
Which is about 0.636619. So what that means is if you take the average of the first in terms of the sequence and you let it grow infinitely large, that average gets closer and closer and closer to this value.
Wow, pi. That's pretty unexpected. So we have this sequence that's tied to these complex transformations, prime factorization, and now even pi. It seems like we've stumbled onto something pretty fundamental.
Pretty fundamental.
So what's next? Where do we go from here in our exploration of A000095?
So now that we have a grasp of what this sequence represents, we can kind of dive into like the more technical aspects of like how to calculate the terms, the formulas and computational methods involved. And that's where things get even more interesting. It really is remarkable how this sequence, it's like it shows how all these mathematical concepts are connected.
Yeah, we started with this idea of counting fixed points
Right.
on this complex plane, and now we're talking about prime numbers and even pi.
Yeah.
It's makes you think about the underlying structure of it all.
It does, and it really underscores the power of these sequences like A00000095
Right.
to like act as guides to lead us to these really unexpected connections.
So as we explore further, what aspect of A00000095 should we focus on next?
Oh, we touched upon the multiplicative property, but let's kind of delve a bit deeper into like the formulas and the computational methods involved.
Yeah, let's unpack these formulas a little bit.
Yeah.
Can you demystify some of these symbols for us?
Certainly. So to calculate terms in A00000095, we need a clever way to determine certain properties of prime numbers.
Okay.
And that's where this thing called the Legendre symbol comes in.
Okay.
It's denoted as A, where A is an integer and P is a prime number.
Okay.
And basically it tells us whether or not A can be expressed as a square of another integer modulo P.
Okay.
So in simpler terms, it helps us determine if a number behaves like a perfect square when we do calculations, only considering the remainders after dividing by P.
So how does this relate to calculating terms in A00000095?
Right. So one of the formulas for AN involves taking the product of 1 plus the Legendre symbol of minor 1 and each odd prime factor of n.
Okay.
So essentially, this is incorporating information about whether or not minor 1 acts like a perfect square modulo each prime factor of n.
So it's fascinating how we're weaving together all these concepts from number theory to understand these fixed points of modular transformations.
Precisely. And the Jacobi symbol extends this idea to composite numbers. So it's like a generalized version of the Legendre symbol, allowing us to work with numbers that are not necessarily prime.
So we can analyze the sequence even for numbers that have many prime factors, not just prime numbers themselves.
Exactly.
That seems crucial for understanding patterns and things like that.
It is. And you know, the OEIS entry provides these code snippets, different ways to implement these calculations. You know, they're like recipes for different programming languages.
Right. Yeah. Like a Maple code snippet.
Exactly. So the Maple code defines a procedure called A000095 that takes an integer as input and returns the corresponding term in the sequence.
That's super useful.
It is.
It allows anyone to really explore the sequence and test out its properties.
Absolutely. And the Mathematica code provides like an alternative implementation.
Right.
So it shows you the flexibility in approaching these calculations.
So we have these formulas and these code snippets.
Right.
But how do they actually help us understand the behavior of A00000095?
Well, so they do allow us to compute terms efficiently, which is helpful.
Right.
But they also allow us to explore patterns and make conjectures about the sequence's behavior more broadly.
Right.
So, for example, we could use these tools to verify the multiplicative property for larger and larger values of.
Right.
Or investigate how the terms are distributed or how they grow or other interesting questions like that.
That kind of brings us to the question of, like, why should we care about the behavior of A000095 beyond just the inherent mathematical curiosity?
Sure.
Is there like a practical application to all of this?
That's a great question. And it's one that, you know, mathematicians often ponder. You know, while the sequence itself might seem abstract at first glance, you know, understanding its properties could have implications for other areas of math.
Okay.
Potentially even in fields like cryptography and coding theory.
So it's like we're exploring this new tool.
Right.
And its potential applications are still unfolding.
Exactly.
We might not know exactly where it's going to lead, but the journey of discovery is pretty exciting.
Exactly. And that's part of what makes the study of integer sequences so fascinating.
Right.
We're constantly uncovering these new connections and potential avenues for exploration. You know, who knows what secrets A00000095 still holds.
Well, on that note, let's delve a bit deeper into some specific avenues for research and exploration that you find particularly intriguing. What are some of the open questions or unsolved mysteries surrounding this sequence? We've really gotten into A000095, these last two parts. You know, explored connections to modular transformations, prime factorization, even pi.
It's pretty amazing.
And started to unpack some of the tools and techniques used to calculate the terms in the sequence.
Right.
I think it's time to take a step back and consider the bigger picture.
Sure.
What does it all mean? Why should our listeners care?
Yeah, it's a good point. sometimes we get so lost in the details that we lose sight of that bigger picture. I think, for one, this sequence illustrates the elegance and the interconnectedness of math, you know?
Right.
At 000095 is a reminder that even seemingly simple concepts like counting fixed points can lead to profound insights and unexpected connections.
It's like we started with this single thread.
Yeah.
And we just kept pulling on it, and it unraveled this whole tapestry.
I like that analogy.
We've gone from the complex plane
Yeah.
to prime numbers to pi.
Right?
All because of this one intriguing sequence.
Exactly. And beyond its, aesthetic appeal, understanding sequences like this can have practical implications as well.
Okay.
So, the study of modular forms, which are closely related to the modular group we talked about, has applications in areas like cryptography and physics.
So the knowledge that we gain from exploring these abstract mathematical objects could have implications in other fields.
Absolutely.
In ways that we may not even be able to anticipate right now.
Right. It highlights the power of pure math.
Yeah.
To drive innovation in unexpected ways.
Now, we've mentioned several related sequences in our deep dive. Is there one in particular that you think would be worthwhile for our listeners to explore?
I think A000089, the sequence that counts the number of divisors of a number, would be a great follow-up.
Okay.
It's a classic sequence. It ties in nicely with our discussion of prime factorization.
Right.
And it kind of offers a gentle introduction to more advanced concepts in number theory. So it's like a stepping stone to even deeper dives.
Yeah, like we're building out this whole network of interconnected sequences.
Exactly.
And each one is kind of shining a light on a different facet of this mathematical landscape.
Right. And the OEIS provides this amazing roadmap to guide our exploration.
So as we wrap up our deep dive into A000095, what is one final thought or question that you'd like to leave our listeners with?
Well, I'd like to encourage them to think about the modular group and its connections to other areas of math. We touched upon its relationship to elliptic curves.
Right.
But there's so much more to explore there. For example, how might the modular group be used to classify different types of elliptic curves?
Okay.
How does this relate to other areas of mathematics like algebraic geometry and topology?
Those are big questions.
They are big questions, and those are questions that mathematicians are still actively investigating. And the answers could have profound implications for our understanding of the universe.
That's a fantastic challenge for our listeners. So until next time, keep exploring the world of integer sequences. You never know what hidden treasures you might uncover happy diving.